Hello and welcome to this video on the first gasp of life for a star, hydrogen, and how it, like all stars, gradually burns out. Unlike celebrity-type stars, it does not die from an overdose, but instead from old age and the gradual loss of energy. The reaction of hydrogen in a star such as our own Sun's Sol is what gives rise to all other elements. That is because hydrogen undergoes fusion, that is the conjoining of two hydrogen atoms to create a larger atom. The next obvious step in size being helium, and from there you work your way up the periodic table. And doing this releases energy which we use on Earth in part, and the other part is reflected back into the universe. For this video, let's start with a main sequence star, or in simpler terms, the Sun at the center of our own solar system. A hydrogen fusion, which is effectively a nuclear reaction. Most nuclear reactions we're familiar with are fission or the separation. This is fusion, the joining of, is the primary process that occurs inside of a star, but what's important is that it occurs inside the very core, the center of the star. This is also known as hydrogen burning, although hydrogen burning in this case is something of a misnomer. It's not the kind of burning you might imagine when you think of, say, a combustion reaction in an engine, a fireplace, or similar. Instead, what we're talking about here is specifically when you get two processes going on. These processes are called proton-proton chain reactions and the carbon-nitrogen-oxygen cycle. For the majority of this, we're going to be talking about what happens when you have a precursor to a white dwarf or a red dwarf star. That is a star that's primarily working as intended, exactly like our own. It is important for us to note that we'll get into the details of what happens as the star gradually runs out of this hydrogen it's using for the proton-proton chain reaction. And it's important to be aware of this, as any star, not just our own, will gradually transition from the main sequence star like our own into a red dwarf and then gradually a white dwarf star. And this is indication of its loss of energy and primarily loss of hydrogen to react. What occurs inside the core of the star doesn't necessarily need to be in the dead center of that core. Rather, the whole reaction for the proton-proton chain reaction is relatively homogeneous across the entirety of the core. Understand, you can actually increase temperature by a fair margin, up to 10%, and while you will get nearly a 50% increase in the energy that will be produced, that's across a huge area. So you might only have 1% increase on the very periphery and 10% towards the center. And that difference will make a big result in change in power produced, but understand that's over a very big area. Further to that, we're talking in some instances up to about a third of the Sun's mass being used for this reaction to occur. Understand, not being used all at one time, but being used throughout the life of the Sun. The next matter to talk about is, well, if we have our own Sun reacting this way, you need to consider that our Sun is relatively middling. In fact, arguably it's on the smaller end of things, not admittedly on the smallest end, which is a different matter entirely, but it's still within the range of stars, not particularly large. And this means that we need to look at what happens in larger stars, or at least more massive stars. Massive in terms of mass itself, not the actual size or volume it consumes. For bigger, or at least a higher mass stars, we have the carbon-nitrogen-oxygen cycle. This is a catalytic process, whereas the others are purely fusion. A catalytic is something we use for a lot of things in day-to-day life. For example, the catalytic converter in your car, particularly in the exhaust pipe, does exactly this process, hence its name. But in terms of what's going on inside of a star, it's considerably more complicated, let's say. The first complication is that where you have a relatively temperature-independent process inside of our own star, the same sort of changes in temperature inside a high-mass star will see significant changes in energy production. For example, that same, or at least commensurate, 10% increase in temperature that has a 50% increase in our star would in fact have a 350% increase in the energy produced in a high-mass star. The other key here is that where that same energy production is largely attributed to the 35% of the mass in the star's primarily core, for our own, it's only the innermost 15% of the star's mass in terms of a high-mass star. If you were to compare these as side by side, your smaller stars like our own rely more heavily on the radiative transfer of energy, whereas these high-mass stars rely much more heavily on convective energy transfer. What's important with these much larger stars is that as the energy goes up, the actual area that's reacting shrinks considerably, oftentimes by more than half, going from about 20% of the total mass down to less than 8%. And this is important, mostly in terms of other stars than our own, as our own relies on less than 1% of its total energy production on the carbon-nitrogen-oxygen cycle. But understand, as our star ages and gets older, it will shift over to this process, particularly as it becomes a red dwarf. For now though, let's focus only on the hydrogen side of things, as, although it's useful to know, that's for later on in this video. The hydrogen production processes, as we mentioned, primarily are the proton-proton chain reaction, and that's going to make up the majority of our own sun's energy production for now, and certainly the dominant fusion mechanism. In fact, it pretty much applies to our sun and anything smaller than it. Part of the reason for this is very simply that the proton-proton chain reaction requires a much lower temperature. The range given is roughly 4 by 10 to the 6th power in Kelvin, Kelvin being effectively a universal temperature gauge used in science. We'll leave it at that for now. Understand, we have a whole video on the System International if you wish to see more detail. The carbon-nitrogen-oxygen reaction requires 1.6 by 10 to the 7th Kelvin, and therefore it needs a much higher temperature. The reason why you get the transition from the proton-proton reaction to the carbon-nitrogen-oxygen cycle is that as a star gets older, the core becomes hotter, and so there is a natural shift to favour the carbon-nitrogen-oxygen reaction over the proton-proton reaction. Knowing that, at least in some respects, as our sun gets older, it's going to be relying on those two mechanisms for hydrogen use, we also need to look at what it's doing with all the material that it's making, primarily the helium that's being produced from the hydrogen. In fact, to get something more complex than just helium, you need more than just the sun fusing atoms. In fact, it requires amazing levels of heat, more so we've mentioned so far. And this is really important. The fusion reaction that hydrogen undergoes to produce helium initially accumulates heat in extraordinary quantities, or at least concentrations. However, by itself, that isn't enough. The helium reaction begins most notably once you get a sun moving into the red giant element or stage of its life cycle. That's effectively once it has begun to run out of hydrogen, you have a very hot core, and suddenly the sun itself has to find other ways to react. And this is also known as a degenerate helium core. Distinct and separate from a regular degenerate who looks at anime characters and has an avatar of an anime girl. Instead, this is specifically referring to a sun. By having the helium in its core, along with the high heat and the lack of anything else to react with, it begins to have to react that helium. That reaction of helium leads to the creation of two very familiar elements, that being carbon and oxygen. Noting that this is already leading us back towards the previously mentioned carbon-nitrogen-oxygen reaction. This leads to a weird phenomena where you have multiple layers of reactions going on. In the very center of the core, you have helium, which will eventually be exhausted. But around this helium core that gets exhausted, you'll find you have a helium fusion shell. This shell will basically be sitting around the carbon-oxygen core that was created by reacting all that prior helium that was present. In order to be able to get things like carbon, or oxygen in this case, you need to react multiple helium molecules. Generally speaking, it's called the triple alpha process, and it's basically 3 helium nuclei are all squished together in that reaction and formed into carbon. This can then in turn be made into oxygen, neon, and other much heavier elements further along the periodic table. And this all involves more or less exactly the same alpha process. It just depends on how many helium nuclei are squished into it to lead to these other heavier elements. There is one exception, or at least one major exception to this. That is, elements with an odd number of protons are formed using other fusion pathways, so it doesn't apply to everything that you would see on the periodic table. Beyond our own star, we now need to look at particularly the carbon-nitrogen-oxygen reaction that we mentioned early on. mostly because they apply to stars with a lower mass than our own Sun's Sol. This carbon-nitrogen-oxygen cycle, or CNO cycle as it's often simply summarized as, is one of the two known methods by which this can happen, and it is the primary means by which hydrogen is converted into helium, or at least with regards to a star smaller than our own. Those at the same size as our own Sun or somewhat larger, and typically larger, will rely on the proton-proton chain reaction instead, as we've already described. This is important, mostly down to the fact that it's how those stars are going to generate their helium. Why this is such a interesting and useful fusion process is the way it's catalytic, where with the fusion process for just hydrogen into helium essentially involves just smashing them together and squishing them, kind of like two balls of Play-Doh. This instead involves the use of carbon, nitrogen, and oxygen as catalytic steps, but importantly, unlike a lot of catalytic processes, these same reactants, or catalysts, are regenerated later on, meaning you never actually run out of carbon, nitrogen, or oxygen, but you also get a whole bunch of other material generated, which is useful. Primarily, you get your alpha particles, this being a stable helium, or at least the nucleus thereof, 2 positrons and 2 electron neutrinos. Because of this, you also have your other elements that exist as well. In order to get to that stage, mostly in terms of, say, our own Sun, the Sun will gradually expand. Now, understand, when we say gradually, we're referring to a process that will take billions of years. About 5 billion years. When that happens, it will start shifting over to this latter catalytic pathway, and that is when it's called the red giant phase. During this phase, the Sun will rely less on hydrogen in its core, as it's primarily run out of that, because it's converted just about all of it into helium. And because it no longer has hydrogen, it will now have to change what it's doing. And that process forces the star to expand at a huge rate and to a huge size. And that's the only way it can maintain its state of equilibrium. Theoretically, if we still had Earth at that time and we either haven't destroyed it with whatever means we have, whether it's nuclear weapons, some sort of a K-pop band, or for instance, biological diseases, we won't have a planet anymore at that point anyway, as, well, we'll be well within the range of that expanding red giant. This brings us back to the earlier mentioned process of burning helium, and then the reaction of that with things like carbon and nitrogen, and oxygen to get other elements. When this happens, and primarily relating to the fact that Earth will basically be consumed, it'll basically blow Earth up. But what's interesting is that prior to then, and even now, the energy we're getting from the Sun has a weird phenomenal effect on Earth, but mostly on the water that is on Earth. Essentially, Earth is constantly losing a small amount of water into space, and it's because the very light hydrogens that are in it can basically be pulled away by the Sun, and particularly the various clouds of energy that come from it. This will gradually lead, very slowly, to Earth losing its hydrogen into space, and that will allow for the theoretical generation of a new star in the very, very, very distant future. At that time, well, hopefully, humans will have long since colonized other planets, and if we haven't in 5 billion years, we probably have bigger issues. But also, it's how our own Sun will gradually run out of hydrogen through using it to generate energy, how that use of hydrogen will lead to the production of helium, and the use of that helium will cause a huge explosion in the Sun's volume, and the destruction of our Earth, and eventually the Sun itself. Thank you for watching this video. If you found it somewhat interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.